Okay, so before we get talking about particle motion, we're going to look at a couple of the formulas that we already know. We know that if we have x of t, v of t is going to be the derivative of x of t. A of t is the derivative of our velocity, which is the second derivative of position. And we also know then that the integral of a of t dt will give us our velocity function plus c. The integral of our velocity function with respect to time will give us our position function. Now, a couple of the formulas that we haven't talked about are with regards to displacement. So our displacement is going to be the integral from a to b of our velocity function. And the other equation that we need to be aware of is our total distance traveled. And total distance is going to be the integral from a to b of the absolute value of our velocity function. So our displacement gives us the change from point A to point B, whether we have gone well beyond point B that second, gone beyond point B and then come back to it. And then total distance will give us the point, for example, from A to C, and then from C back to B, which would be our total distance. The last equation that we need to think about is the average velocity. Now, we've talked about average velocity as the change in position, x of b, minus x of a over b minus a. Well, we can also see from the fundamental theorem of calculus that this is going to be 1 over b minus a times the integral from a to b of our velocity. So you can see that you can arrive at that average velocity function by using the fundamental theorem of calculus and the position function. Now, one thing that we need to be aware of is occasionally position can be written as s of t. S of t or x of t, it's the same function. So let's go ahead and take a look at a couple of examples. Okay, so we have a particle moving along the x-axis with velocity given by v of t for the time interval from t equals 0 to 6. We want to find the average velocity. So again, we know that average velocity, and since we have the velocity function, we're going to go ahead and use the integral. So this is on the interval from 0 to 6. It's going to be 1 over 6 minus 0 times the integral from 0 to 6 of v of t dt. So this is 1/6, the integral from 0 to 6 of 3t squared minus 18t plus 15 dt. So now we have 1/6 times the integral of t cubed minus 9t squared plus 15t evaluated from 0 to 6. When we have evaluated this, we end up with negative 18 over 6, or negative 3. Since we don't have any units, we can leave that one. Now, to find the displacement of this particle, remember displacement is going to be the integral from 0 to 6 of v of t dt. And we've already found that, and that is going to be negative 18, which means we've moved in a negative direction 18 units. So to find the total distance, this is going to be the integral from 0 to 6 of the absolute value of v of t dt So in this case, we have two options. We can solve this by putting the velocity function in the calculator using the absolute value, and we're going to find that our total distance traveled is going to be 46. Now, if you don't have a calculator, you need to figure out where the function changes from positive to negative and then back from negative to positive. So with that, we need to factor. So we know that we have the function 3t squared minus 18t plus 15. So 3 times t squared minus 6t plus 5. So we see that we have t minus 5 and t minus 1. So I know that at time t equals 1 and 5 is when my function switches. So I can rewrite this integral, and I'm not going to go ahead and solve this out, but we could rewrite this as the total distance is equal to the integral from 0 to 1 of v of t dt. And we need to do plus, and in this case, this is going to be the integral from 5 to 1. So again, of v of t dt plus the integral from 5 to 6 of v of t dt. And then you could integrate each of these by hand, and you would end up with the positive 46. Now, remembering that if we are changing our limits of integration to be in order, this becomes a minus. This is 1 to 5. And that way we get the absolute value of that. Most of the time when you need to do an absolute value, you will either have a calculator to do this or it will be something you have a graph from. All right, so looking at example D, we have if the particle has position of 2 at t equals 0, what is the position of the particle at t equals 6? Okay, so we need to use our displacement. And again, remember, we know from the fundamental theorem of calculus that the integral from 0 to 6 of our velocity is equal to my position at point 6, at time t equals 6, minus my position at time t equals 0. Well, I already know that this value is negative 18. I'm looking for the position at 6, and I know that I am at 2, which means that I can see that I am at the position negative 16 when time t equals 6. Now, on the reverse side, if we know the position at t equals 6, we can find the position of the particle at t equals 0. So again, we have 0 to 6 of v of t dt is equal to x of 6 minus x of 0. We know that this is negative 18. This will be negative 4 minus x of 0. And so we can see then that x of 0 will be 18 minus 4. And so in this case, our initial position would be 14. Okay, so let's go ahead and look at our second example. So we have a particle moving along a horizontal line with velocity measured in meters per second for time t equals 0 to 10, as shown in the graph above. At time t equals 1, the particle has a position of 4. So when is the speed of the particle increasing? So that's when our velocity and acceleration have the same sign. So in this case, we're looking for when the velocity here is negative, do we have a point where the slope of the velocity curve is negative, which we don't. So that isn't the case that we need to be concerned with. And the second is going to be where the velocity is positive or above the x-axis. Where is the acceleration positive or where is the slope positive? And I can see that that happens from 4 to 6. So I can say that the speed of the particle is increasing on 4 to 6 because v of t and a of t have the same sign. All right, so looking at the average velocity of the particle from 0 to 10, remember that average velocity is going to be 1 over b minus a, so 1 over 10 times the integral from 0 to 10 of v of t dt. So that's going to be 1 over 10, and I need to go ahead and calculate my integral. And I can do this with triangles. So I can see that this area is going to be negative 2. This will be positive 2. This area is also going to be 2. And this area will be 3. So then when I add these up, I have negative 2 plus 2 plus 3 plus 2. So I can see then that my average velocity is going to be negative 1/2 meter per second. Now, average acceleration, just like we can do with average velocity, so average acceleration could be 1/10 the integral from 0 to 10 of a of t dt, but I don't have a function for that. But remember, then that is the same thing as saying v of 10 minus v of 0 over 10 minus 0. These values I have. So I can look up at the graph and I can find what my velocity at time t equals 10 is, and that's 1. And my velocity at t equals 0 is negative 2. So I have 1 minus a negative 2 over 10. And that's going to give me 3/10 meter per second squared. Okay, so net displacement of the particle, that's going to be my displacement. Remember, that's the integral from 0 to 10 of v of t dt, which is going to be negative 2 plus 2 plus 3 plus 2, which gives me 5 meters. The total distance is the integral from 0 to 10 of the absolute value of the velocity, which will then equal positive 2 plus 2 plus 3 plus 2, which gives me then 9 meters.